All right, today we're going to dive into the machine learning journey. We're going to break down exactly how an idea goes from just a bunch of raw data all the way to making a genuinely smart decision.
So let's start with something you deal with every single day. How in the world does your email know what's spam? How does it just magically filter out all that junk? Well, it's not magic, not even close. It's a process. And actually, it's one of the best examples of machine learning out there. Basically, the system has been taught step by step to spot the telltale signs of a spam email.
The secret sauce behind that spam filter, it's a technique called supervised machine learning. And honestly, the analogy here is just perfect. Imagine it's like a student cramming for a huge exam. You feed the system thousands upon thousands of example emails, and each one is neatly labeled, spam or not spam. It's just like a study guide with questions and answers. And by going through all of them, it starts to figure out the patterns on its own.
So, what is machine learning really? Well, let's get one thing straight. It's a process, not magic. And we're about to walk through that exact process, step by step.
All right, so here's the big picture. The whole journey, from start to finish, really boils down to these 4 core steps. First, you gather your data. Then, you got to pre-process it, clean it all up. After that, you train your model. And finally, you evaluate it, you test it, and you refine it. This 4-step workflow, it's pretty much the blueprint for any machine learning project you can think of.
Okay, so first things first, it all starts with data. These are the ingredients for our digital brain. I mean, literally everything in machine learning kicks off with data. You can think of it like gathering all the ingredients you need before you start cooking. Except here, we're not making a meal, we're building and teaching a digital brain. Now, when we talk about this data, there are 2 really important parts you need to know: features and labels. Features are basically the clues, the input. For our spam filter, that's stuff like who sent the email or certain words inside it. Then you have the labels. That's the answer, the thing you want to predict. In our case, that's the simple tag, spam or not spam. You absolutely need both to get the job done.
So you've got your data, but you can't just throw it into a model as is, trust me. Real-world data is messy. It's got missing pieces, weird formatting. It's a disaster. That's where data pre-processing comes in. This is the cleanup phase, and it is so important. You've heard the saying, right? Garbage in, garbage out. It couldn't be more true here. Having a clean, organized dataset is a total game changer.
All right, our data is sparkling clean. Now it's time for the study session. This is where we finally start training the digital brain. This is where the real learning happens. But here's a key trick. You don't use all your data for the study session. No, you split it up. Think of it like this. About 70% becomes the training set. That's the textbook the model studies from. Then about 15% is the validation set. This is like a pop quiz to check its progress and tweak things. And that last 15%, that's the test set. We lock that away in a drawer. It's for the final exam, to get a truly honest grade on how much it's learned.
Okay, so I keep throwing this word model around. What even is that? Well, a model is what you get after all that training. It's the set of rules, the patterns. Basically, it's what the system has learned, all packaged up mathematically. For a simple model, it really just boils down to 2 things, weights and biases. Now think of weights like a giant control board with thousands of little knobs. There's one knob for every feature, every word, every sender, everything. And during training, the model just learns how much to turn each knob. So a word like lottery, which is a huge red flag for spam, that knob gets turned way up. Its weight is high. A bias is kind of like a master knob that sets a default tendency. It might give the model a tiny little push to guess not spam from the get-go, even before it looks at anything else. The whole training process is just about the machine figuring out the perfect settings for all those thousands of knobs.
Now, one of the most powerful kinds of models you'll hear about is a neural network. These things are incredible. They're specifically designed to find those really complicated, subtle patterns in the data that a simpler model might miss. How? Well, they use these things called hidden layers of neurons that all work together, passing information back and forth, to piece together the clues and come up with a final answer.
So to put it simply, that's the whole ballgame. When we talk about training a model, all we're really doing is letting an algorithm automatically tweak all those digital knobs, those weights, again and again and again until it finds the absolute best settings to make the most accurate predictions possible.
Okay, study time is over. Pencils down. It's time for the final exam. We need to see how well our model really performs. And we're going to do that using the test data, the stuff it's never ever seen before.
Now, the most obvious way to grade our model is by looking at its accuracy. It's super simple, right? It's just the percentage of predictions it got right. If it nailed 95 out of 100, hey, That's 95% accuracy. Sounds pretty good, doesn't it?
But what if a model is 99% accurate and is still completely useless? Yep, you heard me right. How is that even possible? A model with an A+ grade that's actually failing?
This is a classic example. Let's call it the snow in the subtropics problem. Imagine you build a model to predict if it will snow in, say, Miami. Now, snow is ridiculously rare there, so a lazy model could just learn a very simple rule: always predict no snow. And check this out. Over a century, it would be right 36,475 times. It would only be wrong on the 25 days it actually snowed. Its accuracy would be an incredible 99.93%, but the model is totally worthless because it has zero ability to do the one thing we wanted: predict when it snows.
And that's exactly why we need better ways to measure performance. Metrics like precision and recall give us a much clearer picture. Precision asks a simple question. When the model did predict snow, how often was it right? Recall asks something different. Of all the actual snow days that happened, how many did our model manage to catch? For our lazy snow predictor, the precision and recall would both be a big fat 0. Useless.
And there's another major trap to watch out for called overfitting. This is a huge one. It's when the model doesn't actually learn the underlying rules, it just memorizes the training data. It's the perfect student analogy again. It's like someone who just memorizes the answers for the practice test word for word. They might ace the practice quiz, but when you give them a new problem on the final exam, they're completely lost because they never learn the actual concepts.
So this whole process we've walked through, data, training, evaluation, it's the engine behind so much more than just spam filters. So let's peek ahead a little bit and see what's on the horizon for these digital brains. Believe it or not, this same fundamental process is what's driving all the crazy AI stuff you hear about in the news. You've got generative AI, the models that create brand new images and music. Then there are large language models, LLMs, the brains behind the chatbots we all use. And now the next step is agents, software that can actually reason, plan, and take actions in the world. It all starts with the same core workflow.
So here's the bottom line, the one thing I really want you to take away from all this. That process, getting data, cleaning it, training with it, and then testing it, that is the fundamental engine driving every single piece of modern AI, period.
But as these digital brands get more and more complicated, a whole new challenge pops up: interpretability. See, it's not always enough for a model to just give us the right answer. We're getting to a point where we need to know why. We need the ability to peek inside and have the model explain its reasoning in a way that we as humans can actually understand.
And really, that brings us to the biggest question of all. We've gotten really good at this process of teaching machines. So as these digital brains get smarter and more powerful, the real question that we all have to think about is, what should we be teaching them next? What's the most important lesson